this is going to become relevant in the future lab, where actually you're going to end up writing a data structure in OCaml, where you do have to care whether two pointers point to the same. Okay, questions about that? Does that make sense? Okay, and there's also the usual three Boolean operators. So there's an AND operator that's written as 2 ampersands, there's an OR operator that's written as 2 bars, and there's a NOT operator that's actually written as the word not. Okay, so these two act like you'd expect them to, the way they would in, let's say, C or Java or Python. Okay, not works the same way as the exclamation point does in C or Java. OCaml can't use exclamation for not because it's going to use it for something else. It's actually using it in connection with variables, which we haven't seen yet, but we will see later. Okay, but these behave just exactly as you'd expect. And they also work in sort of a short circuit mode, so if I say like false ampersand ampersand something, this something over here never gets evaluated. Again, like in languages you're familiar with. Okay? Questions about that? Does that make sense? Go ahead. So exclamation is not in OCaml, it's the word not. So if I have, if B is a Boolean quantity, I want to say, I'll say not B. Did that answer the question? Other questions? Okay. Let's see, what else do we have here? So integers. Okay, well, integers have a fixed size in OCaml. They're not like Python integers that actually, you know, they get bigger if needed, and they just use the underlying arithmetic that's in whatever computer you have, but with sort of one weird little difference. Okay, so let's imagine that this is a word in memory. Okay, and so let's imagine we're using a 32. Let's say we've got a 32-bit computer. It's a computer with 32-bit words. Most computers these days have 64-bit words, but let's say we've got a 32-bit word. Okay. Well, here what happens is we can number the bits from 0 to 31. This is bit 30 right here. And what happens is that this bit is not used. Or at least it's not used to represent an integer. Okay, well, what is it used for then? All right. The idea is that OCaml has a garbage collector that gets rid of objects that have no pointers to them. And so this is used by, let's say, the GC, the garbage collector. Okay, the way that a lot of garbage collectors work, maybe even all garbage collectors work this way, is that every object in memory has a little tag attached to it that says whether or not that object can be reachable by following pointers from things we already know. Okay? And so the way the garbage collector works then is when we run out of memory and we want to get rid of garbage objects that are no longer accessible. The garbage collector traverses all these pointers and it sets the tag on the objects it can find to indicate that those objects are not garbage, that we can still get to them. And then at some point it just gets rid of all the objects that are not marked. Okay, well, that's what's happening here with integers also. OCaml is using the uppermost bit as a tag and to represent the fact that that integer is not garbage, that it's still being used. Presumably the bit is 1 if it's not garbage and 0 if it isn't. Well, what does that mean? That means that we can use only these 31 bits here to represent an int. So this actually represents the integer. And so what that means is on a 32-bit computer, what happens is we have a range of integers from, let's see if I can write this, minus 2 to the 30 to 2 to the 30 minus 1. Okay. In other words, there's one less positive integer than there is a negative. There's one more negative integer than there are positive integers. Okay, why is that? Well, the way that modern computers represent integers is by using bit patterns in machine words. And it reserves half the bit patterns for negative numbers and the other half for non-negative numbers. But 0 is a non-negative number. So what that means is that one of the bit patterns that represents non-negative numbers is used for 0. That means there must be one less positive number than there is a negative number. Now, for those of you who did not understand what I just said or don't care about it, in practice you don't need to worry, because the sizes of integers are large enough that for most practical purposes you won't run into cases where you have an integer that's too big to represent. Okay? Certainly not in this class. But there is an upper limit on integers. And if you've got a 64-bit machine, which is what most people have, let's say this is, trying to make this integer twice as big. Okay, bit 63 then is used for garbage collection. And so then you get minus 2 to the 61 up to 2 to the 61 minus 1. Again, a fairly big number. The way you can, there's a useful thing you can do with powers of 2. 2 to the 10th is about 1,000, 2 to the 20th is about 1,000,000. Okay, so 2 to the 60th would be like 1,000,000 times 1,000,000 times 1,000,000. Okay? Again, you don't care about that, don't worry about it. Integers are big enough that you'll almost never actually run out of, you'll never run out of bits for integers. Okay, and we've got all the usual operations, plus, minus, star, divide. There's also a mod operator that is the remainder after division. That's the same as the percent operator in C or Java or C++. And, okay, and there's also a whole bunch of logical bitwise operations. Okay, that work on, and they work by adding and oring bits together within an integer or by shifting the bits. We're never going to use those in this course, but if you're curious about them or about how they work, they're described in that icky textbook that I have linked from Canvas. Okay? Questions so far? All right, and let's see. So the next one I wanted to talk about is float. We've already seen some of these already. This just uses whatever this uses the floating point arithmetic provided by whatever your computer is. And probably most computers these days use IEEE standard arithmetic, which is probably almost certainly what you will get. And like we've already shown here, the operators for floating point all are followed by these annoying dots. So plus dot is the operator that adds two floats. And there's also a couple of functions here called int of float that turns a floating point number into an integer, a real number into an integer. We have a function called float of int that takes an integer and turns it into a floating point. Okay, and the word float just basically means an approximation to real numbers. That's a term that originated, makes sense only historically. It used to be, in the early days of computing, it used to be that computers didn't have real numbers built into them directly, didn't have real arithmetic. And so what people used to do when they wrote programs is they would figure out where the decimal point should be in their numbers, and then they would just always arrange their arithmetic so the decimal point never moved. That was called fixed point. This was fine in the early days of computing because everybody who used computers was a mathematical genius. But as soon as people who are not mathematical geniuses started to use computers, people discovered they wanted something that was simpler to use. They wanted a way to figure out where the decimal point should be so it would move around. That was called floating point. So the idea is the decimal point would float or it would move around. And that's the reason that in a lot of languages, float is used to mean a real number. But, you know, if you went out on the street and asked people, you know, what do the words float and real have in common, most people would not know the answer unless you just happen to be lucky and find a programmer. Okay? More than you wanted to know. There's some other operations on floats also. There's an absolute value function that we already saw. Okay, and then finally, almost finally, there's a string. And a string is just a, I want to talk about characters first. There's a character type. And characters are ASCII characters. As if you don't know, what's ASCII? This is an abbreviation for American Standard Code for Information Interchange. It is an 8-bit character code, and it is basically designed for American English. Okay? So ASCII is, and ASCII is not something that you would use to unlock donkeys, for example. Maybe another interpretation. Okay. This is, in my opinion, a problem because this is a very old character set. It dates from about 1967. And like I say, it's designed for American English, and it's pretty good for American English, but it's not very good at all for other languages. And so what happens is that most modern programming languages, instead of being based on ASCII, have used something called Unicode instead. And okay, so there's about 2 to the 8th or 256 possible ASCII characters. Well, in Unicode, there's about 2 to the 21st, about 2 million possible characters. And Unicode is designed to deal with every language that is now or has ever been used by humans. Okay, so All right, so, things like, even languages that don't use the Roman alphabet, Asian languages, languages from the Middle East, things like this, those are all in Unicode. Now, this is really curious because that OCaml would be forced to use ASCII because it's a fairly recent language. It dates from the 1990s. And all the other programming languages that were designed in the 1990s were based on Unicode in one way or another. Java is, for example. Okay? It's even weirder when we think that OCaml was designed by a bunch of guys from Europe, where people speak a lot of different languages, not all of which use the characters from American English. So why didn't they use Unicode like everybody else? I don't know the answer to that. But that seems really curious to me. Okay? And we can do the usual things with characters. We can test them for equality and so on. Characters are written using single quotes. So we can write something like that to mean the character X. Okay, don't confuse that with quote X, which means something completely different. That's a formal variable that represents a type. And there's also a way to represent characters that don't have printed representations. And that's in Hickey also. I don't know that we'll need to mess with that in this course. Maybe we will. Okay, and finally, for built-in types, there's a type called string. And this is just an ordered finite sequence of characters. In other words, ASCII characters. And it's written using double quotes. So there's an empty string. And then there's, of course, a non-empty string that's got more than one character in between the quotes. And strings are immutable. Okay, so you can't go in and change the characters. Old versions of OCaml had mutable strings. I'm not sure why. But the modern versions of OCaml have got rid of that. And you can do the usual things. You can do usual things with strings, so that if S is a string, you can say S dot J in parentheses to get the Jth character. Characters are indexes started indexing. Let's try this again in English. I'm having brain problems today. Characters in a string are indexed starting from 0. Okay, so hello is character 0, 1, 2, 3, 4, like so. And there's also some operators. You can say string.length, get the length of a string X. This notation here is actually refers to something called a module. Functions in OCaml are arranged in modules, which are kind of like classes. And if you want to, so there's some things that you have to use the module system to get hold of. So this is basically saying, go to the string module, get me the length function, apply it to X, and it will tell you how many characters are in this X. And we'll talk about modules later. We'll also talk some more about how strings work later. Okay. Questions so far? Pretty much all of this stuff is built in. Yes?
Is the S when calling the string module capitalized?
Yeah, that's a capital S, because module names begin with uppercase letters. But yeah, that's a good question, by the way. Length, however, is a lowercase l. Other questions? Oh, go ahead.
What do you mean when you wrote ace and float?
Those are the names of functions, and they turn floats into integers and integers into floats. So float event 1 is 1.0, int of float 1.0 is 1. Because OCaml distinguishes between integers and floats, and it does not automatically convert one to the other. That almost certainly answered your question. Other questions? Go ahead.
Does OCaml and like the floats support infinity and negativity?
It does if the arithmetic on your computer does. And I imagine that your computer is using, what is it, IEEE 752, is it? Is that the number? 754? Yeah. That arithmetic system actually does support infinite and undefined and not a number, real numbers. And so I'm gonna say yes, unless you have some weird computer that isn't doing IEEE arithmetic. But I'm not sure what the right answer is. I'm not sure if I can give you a better answer than that. Other questions? Okay. All right, and sort of the last type, built-in type that I'm going to talk about is list. And eventually we're going to get to the point where we can start talking about defining our own types. In fact, today we're going to do that. So if I say t-list, this is the type
character string
of a list whose elements have type t. So for example, if I write int list, I get, that's the type of a list of integers. If I say string list, I get the type of a list of strings. We've already seen some stuff about how lists work, okay? And note that type names in OCaml are actually postfix operators. So they have a single argument at the beginning that's telling you what kind of type you have, and then there's a name that follows them that. Let me say that in a different way. There's an argument in the beginning that tells you what is contained inside that type, and then there's a name after it that says what the type actually is. So it's like a postfix operator. Okay, and those can actually be defined by us. We can define our own. Types, and that's one of the things we're going to talk about, if not today, then next time on Friday. Okay, so that was just a really quick overview of types. There's a couple of other types we'll get to later in the course. OCaml has an array type, and a variable type, and a record type, all of which are mutable. And we'll get to those as we need them. Okay, so I'm about to describe pattern matching here, but for the moment. But any questions about anything else before I do that? Okay. So, what we had before, remember, is that we had these functions head and tail that worked on lists. And we've got these functions first and second that work on two tuples. Okay, I talked about two